Okay, yeah, good morning. Just doing a video today carrying on with the software for the series on the software-defined radio. I'm quite conscious by the looks of it that the videos looking at the software side of the house is probably not of so much interest to everybody, sort of just looking at the feedback and the like. So I think it's quite important to continue going down this road because for me it sort of helps explain which was the whole idea of the series, of sort of putting it together and how it works behind the scenes. So apologies there if it's not of a huge amount of interest to everybody, but I'll sort of try and keep it short and to the sweet, short and to the point. Anyway, so just continuing on, this is a phasing receiver, and there's certainly a whole lot of material on the internet on how these particular receivers work, and it's exactly what we're doing here using the Teensy. And here's one particular website. I just sort of quite like this diagram here, so I could use just to talk to it. As we've seen already with our setup in the analog side of the house, we've generated our in-phase and our quadrature analog signals using the NE612 mixers. We'll put those through a simple low-pass filter that's sitting around the -3 dB point, is around 10 kilohertz. And now we have a dotted line through here, which we'll see in a sec, signifying that we're now going to put it into the digital realm within the Teensy and then carry out some digital signal processing. Now the HT here, the Hilbert transform, we'll have another look at that in a sec. The theory here for this whole phasing technique is to generate 180 degrees phase shift between our quadrature and our in phase. In fact, it's going to be quadrature is already 90 degrees out here. We add another 90 degrees to it here, and at this point we can either add it to the other path or we can subtract it from the other path. And by doing either, we can recover our upper side band or our lower side band. Right, so if I now just sort of go across to the Iowa Hills website, this is a gentleman here who was an RF engineer during his working life. He's now retired, and he's generated some fantastic tools here that allow us to design filters that we can then easily, in terms of the coefficients, put into our Teensy program to create filters how we like. So the one page we are going to quickly look at here is the Hilbert transform page. So I can click on that, and it brings out some good information on the Hilbert transform. Now going down here, you'll recognize this picture here. So that's very similar to what we saw before. We've got our quadrature signal coming in, adding another 90 degrees using a Hilbert transform, and then adding it to the other leg. Now, in digital signal processing, with a filter like this, or any filter really, there's going to be a delay. So what you need to do to ensure that the signals arriving at our summer are at the same time, as in this particular case, you have a second filter here which is not actually doing any filtering, it's purely just a time delay. So the time delay here and the time delay there means that the signals arriving at our summer in terms of time are the same. Now there's another way you can do that, which I'm going to do, and that's by using two specialist Hilbert transforms that are not applying 90 degrees, but in fact one's going to be doing plus 45 and one's going to do minus 45, and these will be matched. And the beauty there is, because they're matched, the time delay or the phase delay going through is the same, and overall we get what we want. We get our 90 degrees, in this case it's going through this leg here, plus 45, this one's going minus 45, so in effect we're getting exactly the same here. We're getting 180 degrees between our in phase and the other phase, which is 180 degrees. So that's what we're going to be doing using two 45 degree Hilbert transforms. So again, so this is just an image of what we're going to do for us. basically just summarising where we're at. So we've had our RF come in, it's been split, we've got the two NE612s, we've got our quadrature local oscillator that's mixing with those, we've got our quadrature analog here after the low pass filter, we've got our in phase down here, and as we just mentioned, we're going to implement in software in the Teensy two 45-degree Hilbert transforms, and then we're going to feed that to the summer. And the way it's set up, if we add the two together, we're going to recover our lower side band, and if we invert this one here, and that's very, very simple to do, and then sum them, which is the same as subtraction, we will get the upper side band. So that's the approach we're going to take, and then this little arrow here, we may look at down track adding a second tighter low pass filter with a more restricted bandwidth if we wish to do any kind of bandwidth limitations on the audio. But as you'll see here, I'm going to keep this video relatively short. Just in a sec we'll look at how the software or how the Teensy code's being prepared, and then in the next video we will look at the Hilbert transform design software that we need to generate the coefficients that we then pull into our Teensy program to in effect create these two Hilbert transforms, and then we'll look at the performance of that on air. So we'll actually tune her up and we'll compare this very simple setup between the radio we've got at the moment and a commercial radio. So we'll just break here and we'll have a very quick look at the code, and then we'll break there for this particular video. So here goes the code that we're going to be using on the Teensy, and all I'm going to do here is just quickly go through and just show you how it's been set up ready for the coefficients that we'll design using the Iowa Hills design software. So all we added up here is an area here where we're going to place our coefficients. So at the moment it's a null matrix, and in there very shortly, all through here, we'll put the coefficients. I haven't worked out yet, and we'll do that in the software, how many taps we're going to use on that. But whatever it is, we will define up here as a define. So the number of Hilbert coefficient taps, and that number then will be used down here to define that particular a matrix here. Now going down through, we have to define a couple more objects. We're going to be using audio or the FIR filters that come with the Teensy audio library. We're going to use two of those, and we're just going to notionally call them for the receive side of the house Hilbert plus 45 degrees and the Hilbert minus 45. So if you recall from that image, we've got two of these filters, one for the plus and one for the minus. We're also going to use a mixer, and you recall from the previous video in the terminology used by the Teensy audio library, a mixer, a sound mixer, essentially sums together different sounds on the input and then sends on the output that summation. So for us it's a summer. So I'm going to call it here, just make it a bit easier when you're reading the code, receive summer. Had to do a little bit of manipulations here on the audio connections. You just recall that sort of patch panel with cables. So now our audio input, we've got our left and our right, our 0 and our 1. And you can see the 0 one is going through to the Hilbert transform plus input, and the audio 1 is going to the minus input. That should be a 0 for the input, not a 1. That's a mistake. And then the output of that particular, the plus 45, is going to one of the inputs of the summer. It's going to 0. And the minus 45 degree, the other Hilbert transform, is going to port number 1. So that's a 4-port. We're only using port 0 and 1, 2 and 3 we're not using. And then the output of that summer, we're then feeding through to the audio output. Remember, this is a mono output going through to amplifier, so it's just going straight out. So that's effectively now we have, using these audio connections, hooked up the software to function like the block diagram. What we've done here also in the setup area of the code have basically just had calling a function called turn on receiver. This will eventually be a transceiver. So when we first run this program, we want to basically turn on the receiver. And what that does, here goes the function here called turn on receiver, nice and short. All it's doing is it's enabling the input, audio input line in, so that's the audio coming from our two NE612s. We're notionally keeping the input line level at 5, that's the default. If you go and have a look at the Teensy audio library design tool, that online tool, and you look at the I2C input object, then you can see the various levels that you can assign for that. And in the process, I'm also unmuting the headphone jack, because we're using the headphone jack to feed audio out to our external audio amplifier. And here we are beginning. So that's one of the attributes for these two filter objects. So there goes our minus and our plus, dot begin, and then we have to tell it what the coefficients are and how many there are. And you'll recall these Hilbert plus coefficients and a number that comes from the very top, where we're eventually going to populate these two areas here with all those coefficients. So those coefficients are used in setting up or beginning those two filters. And also in terms of turning on the receiver, we're also working out, and at the moment I'm not using, and later on we can certainly use that, but at the moment I'm not using an external upper sideband, lower sideband switch. I'm just purely using the logic. So in other words, I'm ignoring the new 60 meter band, which is upper sideband. But for me here at the moment, anything less than 10 megahertz is going to be lower sideband. So what I want to do then for those two inputs, so if you remember that RX summer, we can change the gain. I spoke about that in a couple of videos back. So for port 0, we want it to be multiplied by 1, so full on. And for the second input, also 1, so full on. If, however, the frequency is above 10 megahertz, then we want to use upper sideband. So we don't muck around with the input on 0. We keep that at positive 1. But you'll note here we have a slight difference. We've now made the second input, which is notionally input number 1, we've made it negative 1. So it's full but inversed. And because it's a summer, if you're summing a negative number, then it's effectively subtraction. And that's how we'll recover our upper sideband. And that's it. No other changes at all. So pretty straightforward. So all we need to do now is we need to go and use that Hilbert transform design software, and we're going to design a couple of filters that we think may work, and then that'll produce a whole lot of coefficients, which will then I'll show you how we set those up, and then we will suck those and put them between these two brackets here and populate these two, and then we can compile, load it up, and we'll do some tests using the radio. So I'm not going to do any more than that. Apologies if it's a bit dry, but unfortunately that's just the way it is with the software. Any questions, sing out. Any comments, please sing out. If there's anything I can do to make this more useful, noting that I'm no expert in this, please sing out, and we'll go from there. So anyway, 73s, and like I say, the next video we'll be looking at designing those two filters. We'll see you then.